Welcome everyone. Uh, thank you all for taking the time to join us today. My name is Nikos Karagounis. I'm the founder and director of Prosomiono, representing Altair as channel partners for engineering simulation tools. I bring a technical background with a bachelor degree in mechanical engineering and a master in advanced product design engineering and manufacturing. I also have several years following and professional working in the engineering software industry as application engineer and technical consultant before that. I will begin today's webinar with a brief overview about the UAV market and the vision of its future. Following this, my colleague Georgios Tsolakidis will continue with the technical presentation, diving deeper into how our solutions support UAV development phase. So let's start with the bigger picture about the global UAV market, which is currently about 36 to 41 billion and forecasted to triple by 2032. Now, over than 7,500 companies are operating in the field, and with more than 150 focusing specifically on AI-driven systems. UAV technology is no longer confined to niche applications. Over 100 countries are now integrating drones across diverse sectors like agricultural, defense, infrastructure monitoring, environmental, and more. And imagine that the last year, over than 10 million drone deliveries were successfully completed worldwide. This isn't just a growing market, it's a market transforming at a scale and a speed. About the next generation UAVs are rapidly evolving with advanced technologies like hybrid population, AI business autonomy, and morphing airframes. This innovation introduced complex performance challenges that can now only solve through sophisticated engineering simulation techniques. From fluid dynamics and thermal modeling to digital twins and swarm behavior prediction, simulation is now essential in UAV development process. This slide highlights how many use cases, pains, scenarios can you predict with the right engineering simulation tool to avoid failures, costs, and improve your products. But of course, simulation alone is not enough. What truly makes the difference is a robust engineering process, the right expertise, and the right technology partner like Altair and Prosomiono who understand your business and guide your team in every step. On this final slide for my quick presentation, you will see a snapshot of Altair holistic simulation ecosystem designed to support the full spectrum of UAV R&D from concept to production. Imagine structural analysis to aerodynamics and from electromagnetic to manufacturability. Altair have the tools and the methodologies to accelerate your innovation and help you deliver UAV that are not only cutting edge, but also robust and market ready. Thank you again for your attention. I will hand it over to my colleague Georgios, who will guide you through the technical demonstration by showcasing our technologies, practice on and elevate how we can help with the UAV development initiatives. Georgios?
Thank you, Nikos. That was some interesting numbers from your side. My name is George. Today we have prepared a presentation for you regarding multi-physics platform from Altair and our solutions for UAS, unmanned aerial systems. So our main focus here today is to give you a brief presentation regarding the importance of simulation and the variety of physics that are involved in this type of technologies, from structural analysis to electromagnetics to CFD, moving to when we can use AI or machine learning techniques in order to achieve our goals. So let's start with some trends. What are the trends? These are all the goals, let's just say, from a company perspective that wants to achieve in order to make its product better and better. So these are well-known trends. As you can see in this slide, we have fully autonomous systems, range and more applications. These are all very important aspects of our products. On the other hand, all these systems are very complex and require advanced modeling in order to study them deeper. So versatility is another aspect that always has to be acknowledged, like when we can think of a scenario where we want to increase the range of a drone, but we don't want to compromise our safety or the payloads, another aspect of its performance. So the role of simulation. A common question is when to simulate and what to simulate. These four pillars, I believe, are the most appropriate ones. Design, we have to include simulation within the design process early on the stage of the product life cycle in order to get the information and to know in which direction we have to go in order to make our product better. Then there is verification, of course. In this type of systems, we have to follow rules and pass some tests, some validation cases. Another important aspect is manufacturing, how we are going to build this product, how we're going to do the fabrication. Is it feasible? Is it sustainable? This is a very common issue that we don't see it until the end of the design. And then there is, of course, operation in which we are going to see the performance of what we design, what we built, and simulation is a critical point as well for this stage. Now, I talked about the design-driven simulation, where the typical design process includes the development concept and then the detailed design. This can be troublesome, prone to errors, and this is what Altair offers, the simulation-driven design. We have to do our optimization, our manufacturing, our structural analysis all together within the design process in order to speed up and to be more sustainable, in order to go to a prototype, validate it, and go to production. As we can see in this slide, there is a timeline, what tools we use, what techniques over the years. We started from a little bit of simulation. We go to 3D CAD. That's the first digital prototype we had. We designed it in our computers, in our laptops. And then today, we are in a position to do not only simulation-driven design, but data-driven design. This is a very good aspect of this today. Now, if we want to do an overview of how a smart drone development would look like, we have the physical space, and then we have the digital space, where we start from the concept formulation. We are trying our ideas, see what they go as, and then as a simulation-driven design, we include all the simulation, all the physics at this point in order to go to the detailed design. As you can see, there are a lot of physics involved, a lot of software usually involved, but the goal is to achieve our aim, not to how many tools are we going to use or how many physics are involved. Then after the detailed design comes the product release, the manufacturing, the validation of our product, some physical tests in order to see what we fabricated, And then there is the first feedback we get from what we designed to what we fabricated. But the cycle doesn't have to stop at this point. We can go further, and until the end of life of this product, we have digital twins, we have hardware in the loop, simulation in the loop. There are a lot of other aspects to take in account. Before we go deep into 3D modeling, structural analysis, CFD, hot topics, of course, we're doing some math, some system level simulation. For example, in this scenario, we have from electric circuit to motor dynamics to multibody dynamics to some control systems in a schematic. All of this can be translated into a co-simulation within Altair in order to produce a scenario. In this case, the scenario, as we're going to see in the next seconds, is how a drone is going to deliver a package in an urban area, as we all heard about. This is a schematic behavior of what the co-simulation would look like, high fidelity models with low fidelity models all together in order to do a scenario, in order to create our embedded code for flight simulation in this example. In this type of topic, for example, we have Kappa Electronics that they, and I'm quoting its owner, they were not so sure if and how they could do this simulation for their customers. Altair provided the appropriate tools in order to work seamlessly and create a quick and accurate simulation. Now, structural design is a very common concept. We all heard about it. Some of us are doing it in our day-to-day work. It includes multibody dynamics, some thermal in order to test the different electronic and systems that we have in a very compact way within this type of technologies that may have a temperature rise, some structural analysis, of course, in different parts in order to go to a multi-physics simulation. In order to test all of them together, not integrate results from one to another that can cause some errors that we have seen in the past. Then there are some more niche simulation, but essential to how we construct, how we fabricate, what our goals are for our products, like impact analysis, drop test, some optimization, which is not to be neglected, DOEs, and how we are going to manufacturing our product. In the same manner, simulation-driven design means essentially what you see in these 6 pictures. We start from the initial CAD model, and then we define our constraints, our loads, our design base in order to start the topology optimization to reduce the mass without compromising its stiffness, and create a generative concept like this one, which can be more robust than the initial one in some ways, and can be sustainable, can be more performance, can have a more robust performance. Then there are CFD. Okay, this is also a very well-known simulation. We're going to see the aerodynamic behavior of a product, aeroacoustics, noise that has to do with some verifications, thermal analysis, as I said before. All of these are high fidelity models in order to get our results, to go to a more deep understanding of what we designed. A very common example of this for everyone, which is from the CFD standpoint, is how we're going to optimize our design. A nose optimization we see on the right, or an engine inlet. We have to reduce CD coefficient of drag. We have to ensure lift is as it should be. We have to study turbulence in order to understand fully the phenomena. But this is a high fidelity model. Okay, I want you to think this type of scenario where the structural team of your company owns just the stresses, just the pressures, to test some angle of attacks in order to redesign something or reconstruct something. Wants to know how it's affecting the overall performance. A high fidelity model is not always preferred due to the fact that this is a very time consuming application. It needs some expertise, and of course it's necessary, but not on always all stages, all phases of our design. In this example, we're going to see low fidelity models, high fidelity models, and mid fidelity models. As you may know, Euler codes from vortex lattices, RANS, LES, DNS, we have to choose what's the appropriate solver for our scenario. Here comes panel methods. Most of the time, this specific software, Flightstream, is extremely nice for the communication between the CFD and the structural analysis teams in your company, due to the fact that it requires a very small amount of time without compromising the accuracy of our results. And the flow regimes is in all spectrum. We have incompressible flows, subsonic, transonic, supersonic, even hypersonic in some cases. So I want you to feel that not always we have to do a high fidelity model even before the detailed simulation. This is a well-known use case in both academics, where we introduce mathematical models, and we are trying to avoid sometimes high fidelity, fully turbulence modeling in our case. Then we have crash, safety, impact. These are very essential in the destruction of our product, or the worst case scenario, let's just say, where they're going to be a drop test or head impact in a test, a bird impact, also in tests. These are simulations that are niche, but Altair has showed the way in this field a lot of years with its specific software. Multi-body dynamics is also something to not neglect. In this case, we see how we see phenomena like pitching, rolling, the movement of different parts of the system. This is essentially something that I believe in all tests, in all prototypes, it has to be achieved in order to see how we actually communicate with our product. Does it do something that we didn't say to do? This is very good approximation to do it in a simulation environment, to know beforehand how it should affect our product. Another example using multi-body dynamics is morphing of the wing. Here we see movements well known in wings, like pitching, rolling, yaw, maybe some plans or surge. We have to know and understand through some mechanical parts like actuators, how to move our wing in order to get the power requirement, to reduce the power requirement or the fuel consumption. This also a very good approximation in order to know beforehand what should we do, what we should design, and things like that. Here's another example of a Eurocopter where there was no space in order to get the flight measurements, and of course it was a necessity, let's just say, to go to what if studies in simulation scenarios and improve our design. Another hot topic is the weight reduction in order to get the payload we want to at the end of the day. Essentially, we use composites in this type of structures, and we have to not only use composites but to study them deeply. This specific case show us from Earth aeromorphology that they achieved 50% weight reduction, which is a very good number to aim, let's just say, by doing some structural analysis, some composite analysis within the same software, and then some DOEs in order to get the best of it. So composite analysis, optimization, we want to reduce the weight, but we have some safety constraints, and we are also having some manufacturing constraints, like what would be the thickness or how we are going to stack the plies in order to be manufactured, the feasibility of this operation. As we are going to see in the next slide, Altair, as an industry leader in structural optimization, includes a broad framework for optimization. Like, we start from the design concept, where when we are doing some topology, like we saw before, some lattice beams, we include manufacturing constraints, how we are going to fabricate our product, or a part of our product is going to be extrusion, is going to be form. These are all parameters included in our optimization framework. Then we have, of course, lattice. If we want to do something more futuristic, gain some pros from this operation. Of course, topography optimization in order to understand the topography of what we designed, to see repetitions, to maximize the surface characteristics that we want to do. Then there is shape optimization, well-known optimization sector, let's just say. Size optimization, in this case, this photo is a very good example from Airbus, where we wanted to do a size optimization regarding the air duct frame to reduce the weight. And then there is composite optimization, where we have reshape, size, and stacking, as we're going to see in the next slide. But we don't stop there. We have DOEs, stochastic methods, in order to get the best of it, get a large set of manufacturing constraints, and see our responses. So composites, we're going to see in the three-phase how we are going to optimize it. We start with our initial design. We know we want a composite. We start with free size optimization. Was the more efficient way of ply shapes that we want to do. Here you can see a ply slicing in order to get a visual idea. Then we have size optimization, how many plies in order to get the maximum thickness of the material and meet the engineering targets. This also a very good video of how we are doing size optimization. We want to define its ply, its thickness, and then we move to shuffling, where it's the most crucial part, I believe, from my opinion, how we are going to do the stacking in order to be manufactured, to be feasible for manufacturing. this a good example of how what different scenarios we can determine in order to get the idea of what's the best scenario to go. Uh, I said a few times manufacturing, and someone would say, what's he talking about? What manufacturing has to do in simulation? Altair, as one of the few international vendors of simulation software, includes manufacturing solvers. Like we want to study, we want to simulate the process itself, like you see casting, metal forming, extrusion, or 3D printing. These are all solvers and not some fancy videos in order to study the manufacturability itself. This is a very good example as well, where Aeroshift wanted to 3D print the frame of its UAV and used our simulation tools in order to reduce the development time, reduce material waste, going to sustainability. Another aspect of simulation now, we have electromagnetics, a very common issue that can be that can occur in our tests. Essentially, UAVs are flying RF systems. Everything has to do with control and detectability. So antenna placement, as you see, to reduce interference, to radio coverage or jamming, or how the signal goes in place. These are all very essential simulation that we can do and we have to do. Here are some more specific areas where we introduce some software like Flex for motors and sensors, FECO for antenna placement, and WinProp for radio enforcement for urban or mountainous environments. These are all work seamless. This is a very interesting point to point out. And then we have our electronics from a PCB level. We want to reduce the PCB design iterations to get the best of signal, power integrity, thermal distribution. These are all within one software for you to test, to verify, and then to meet the manufacturing utilities of how to construct this your PCB designs. Here we see a very good example of a camcopter with some very interesting numbers, like 50% of weight reduction, decreasing the time to manufacturing the product by 2 months, and of course time, cost savings both from time and material waste. In this customer story, there were used a lot of simulations, as you may see, like structural analysis, motion, shift-D, and some other tools from Altair portfolio. Moving to AI, to machine learning, I won't go too deep, but it's nice to have an idea of what machine learning or AI has to do with our simulation, our products in this industry. For example, we have some measurements from our design, from our prototype, and we want to include them in a Knowledge Studio workflow, create a machine learning model in order to get the progression, for example, of how the remaining useful life of our product could be, and test it, validate it with our actual data in order to train again the model and understand trends, understand some things that are not used to some engineers beforehand when they design the product. In this manner, Altair has a platform, a specific platform from digital twins with optimized tools to do a specific workflow, but all together work seamlessly, like the data preparation, data modeling, how we visualize our data, our results, how we are going to create the appropriate structure for importing our data. These are all together in what we call Altair RapidMiner tools with some other extra tools from the simulation to work together. So digital twin, this is also a very common term that we hear about a lot of years now. We start from the digital prototype and we want to go to the physical one. This is the first time again where we can collect our data and evaluate them, import them in our design, tell our engineers that what went wrong or what was good of what we designed. But we don't have to stop there. We can continue. We can connect the two assets, the digital and the physical prototype, in order to increase the life of the product, to predict some maintenance. These are all data-driven simulation now, with respect to what we collect, what our experience tells us, all of them in a scientific manner now. So that was from my side. Thank you all for your attention. Feel free to ask, to communicate with us your concerns. Thanks again.
Thank you, Giorgo, for the points. It was very, very insightful. So yeah, about now, as we are in the end of today's webinar, feel free to drop some questions in the chat.
I would like to point out that I didn't want to discuss software names in a general way, because the tools are a lot, but we only care, engineers only care how to solve their problems, not what tool should we use. And for many scenarios, for many cases, there is not only one tool to do our job. One tool can go us to a specific point.
Exactly. We have a lot of tools, or more than 150, but we are here to stay close to your team and consult how we can create together an efficient process to work and achieve your goals in your product development.
Sorry, Nikos, we have a question.
Nice.
Yes, congratulations. Any specific detail about control engineering methods, feedback, PID, or advanced methods?
Altair has a specific software for PIDs, for example. This is very similar to if you are working on MATLAB or Simulink in order to do the schematic behavior of control systems. I don't know if this answers to your question. Feel free to further discuss it with us.
And we have one more question. Could you give an example about an inlet optimization? Which technique are you using? For example, geometry optimization or mesh optimization?
An input, you said?
Inlet. An intake, maybe some an inlet fluid flow.
There are some aspects to consider about. We usually do a pre-shape or size optimization in order to understand what would be the gates of our walls of our inlet. This is a very common case in jet engines, for example. Mesh optimization, on the other hand, Altair has one of the best preprocessors, HyperMesh, and optimization of the mesh is within the meshing itself.
Okay, thank you all again, once again, for joining us today. You can have our emails from the chat and stay in touch. Thank you.
Thank you all.